In this video, I'm going to walk through some additions I've made to my SPI functionality. In the last video, I commented that I'd like to get an SD card working. I now have that SD card working down here. To start out, just as a reminder, SPI is Serial Peripheral Interface. And there are 4 lines that I'm working with as I get into this. There's first of all a clock. There is data from my processor, what I'm going to consider the master, out to the different devices, the different slave devices called MOSI. There's data that flows the other way called MISO. And then there's chip selects. So if I want to work with a device, I have to have a select line and pull that line low for that device. And I can only have one chip select low for a given master. And in my case, I'm using a 286 processor, of course, but I've kind of said my master is this VIA device down here. And that's a Western Design Center 6522 VIA, or Versatile Interface Adapter, that I'm using. And I mentioned that a little bit in my last video, where I connected up one of these 8-character 7-segment displays. And I connected that to port B. Well, the other thing I had connected to port B was a nano, so that I could write logging data and see it on my PC screen. I ended up actually splitting that out into port A. So now I have 2 separate ports. Each can control a separate set of slave devices. And the nice thing now is I can use both port A and B simultaneously. So I can have my nano and another SPI device on port B simultaneously going through an SPI sequence. And that's going to be important here, because as I get into adding an SD card, I had to do some troubleshooting, and it takes a lot of detail, I think, to get the communication to an SD card working right, or at least that's been my experience. You got to pay attention to all the little details, but you really kind of need a way to debug and log as you're going. So I wanted to be in the middle of communicating sequences to this card and be able to write to my screen exactly what I'm doing step by step. Well, if both my nano and the SD card were on the same port, I can only have one or the other active at a time. And certain sequences on the SD card, if I deactivate that CS, it basically causes issues with the sequence that I'm trying to send it. So in other words, I have to create the CS low state, send it a whole series of things, and then finally pull up CS when I'm done with all that. I can't pull it up, jump to a different device, write some stuff, pull it up, and come back and drop this down and start working with it again. So I split it out. So my nano is on port A, so I can be writing to it while on port B I'm working with this SD card. And that turned out to be quite nice. So I'm glad that I had 2 ports and could really think of it as 2 separate masters, and each master has its slave devices, which is what you're seeing on the screen. I did run into another problem when I was getting into this. In the last video, I was writing to this 8-character display just fine, and it doesn't have any data that comes back. So there's no MISO coming out of it. So I wasn't able to test reading back SPI data into the VIA. Well, as I got into trying to read back data from the SD card, I did run into an issue. I could not read back the data. I would get all Fs, and so I knew something wasn't quite right. And after a bit of troubleshooting, I came to realize it was a clock problem. And I was using the peripheral clock out of the clock generator up here. So when I bring in my main clock signal into the system, this chip basically takes that in, and then it sends out a clock that's supposed to be used for the rest of the system. The processor internally uses half the clock speed then. And so, like in my case here in this video, when I'm going to run this, I'm running 24 megahertz here. I go through a flip-flop, which means I get 12 megahertz coming into the system, into this clock generator. It sends 12 out, and my processor then internally cuts it down to 6. Well, another output on the clock generator is a peripheral clock, and that peripheral clock is what I was sending down here. And that peripheral clock is at kind of half speed. It's at the same speed as the processor. One thing I didn't realize is that peripheral clock is inverted. So whatever it's sending out for my system clock that goes to the processor, the P clock coming out of this chip is actually inverted. And so what I was running into is that when I'd go to read, the timing just wasn't quite right to work with it with that inverted clock. So for simplicity, what I did, I still wanted to use P clock out of here. I just added an inverter down here. So this is a 7414 inverter. I brought in P clock as it comes out of the clock generator. I invert it and then run it into my VIA. And that took care of the issue. So then I was able to read properly. My goal was to get something on the SD card, some just raw data, and what you're seeing on the screen is the actual raw data that I have on the card that's in this little SD card reader. My processing then, what I'm doing with it is I'm trying to read it through port B, and that's the 286 controlling all that. So it's all the assembly code I'm writing to go out and read from the SD card. And then once I get it, I want to write it out from port A to my Nano so that I can see it on the screen. And what you're seeing here on the screen is what I have done. And so what you're seeing here on the screen is what I've done is I have this, type of an adapter that I'm connecting directly to port B. And again, the pins I'm going to need my clock, I'm going to need my both Mosey and MISO, because I'm going to have to send it commands and get back statuses. And then of course I'm going to have to read back data. And then I had to apply VCC and ground, and then of course a chip select. But this is the data that in my testing I want to make sure that I can pull back and retrieve. And over here to the left is my basically output that I'm sending. So on this Nano, I have on port A the same types of pins, MISO, Mosey, my cable or chip select, and clock. But then once I get that SPI data in, I then send it through the USB over to my PC. And then on my PC, I have this this is just TeraTerm. It's just a serial monitor tool, serial terminal tool. And that then lets me go through and see what's going on here. And then I can write sequences of strings to it and characters. But down here, there's these characters that I can ignore. That's telling me that it actually found data when I get an FE. But then starting at 1D here, this should match everything that I'm seeing over here to the right. And this tells me I was successful, that I was able to go out, get this data over here, and then go through and print out. I just grabbed the first 1K of data. And I'll show this live running here momentarily. So that's what I was trying to accomplish. And this is going to set the stage so that now I can put ROM data, a whole series of ROM images on here if I want, and then I can dynamically load that data, write it to RAM, which is hidden under all these wires, and then actually run code from that RAM. So in other words, I can shadow into RAM whatever is on this SD card. And so all that reading of data now is working. And in a future video, I'll try to then actually just copy it. Instead of sending it out to the Nano, I'll just copy it into RAM and then try to run from that. We'll see how that goes. I would say that doing bit banging of SPI can be really tricky, and you do need some good troubleshooting tools and definitely access to documentation that talks about SPI and the different commands. About a year ago, it looks like January 4th was when I published this blog post. This was when I was working towards getting an SD card working ultimately for my sound card. So I have a sound card I built. It has an onboard SD card. I can store basically music that I generate and save to it. It can play that back from the SD card directly without any external processing. It has its own coprocessor. I was running into quite a few troubles in the process of trying to get that to work, and I captured a lot of information in this blog post. So I'd recommend, if you're getting into this and you want to see maybe some of the troubles I ran into and some of the resources I was using, take a look at this blog post here. And I do link to a bunch of other blog posts that are out there, and there's a lot of good information, and I posted a few of my favorites in that article. One of the resources I've used is this one from rjhcoding.com, and this author is connecting in an Atmega 328 to an SD card. And so all kinds of good information about all the steps you need to go through to do that. And one of the things included is this type of a flow diagram. And you'll find these in a lot of the SPI type of documentation out there, or data sheets for SPI type of devices. But to make it work, and I'm just going to really shortcut this, you have to send it a specific sequence of commands with values that go with those commands. And you have to work your way through checking certain things and getting certain values back. And if it passes this, then move on to the next command. And if it passes that, move on to the next command. And eventually get to the point where you can do something like read data or write data. And for me, these are the commands I'm using. I'm using commands 0, 1, 8, 12, 18, 41, and 55. And actually, I might not be using command 1 currently. So this one maybe I'm not using, but the rest I should be. So right away, as an example, when I first power up, the first thing I have to do is send it a command 0 along with parameters for that command to get it into an idle state. And to do that, I have to send it basically 6 bytes of data. So I'm going to have to send it a 40, a 0, a 0, a 0, a 0, and a 95. And if I send all of that through SPI and it receives it, it should process it and should send me back a status that I can read. For example, I think in that case I'm looking for a status 1. Okay, if I get a 1, I then can continue on to the next thing, which I'm going to call a command 8. And if a command 8, I have to send it these 6 bytes of data through SPI, and then I'm looking for a response, for example, a 1 again. And if I don't get it, I might jump back to command 0 and try the whole sequence again and keep doing that until I get the SD card to properly respond. So those are the types of commands I'm using and the data I'm using, in case you're curious. And then I wrote little procedures that say go try command 8, and if that works, move on to try command 08, or try command 0, then try 8, then try 55, then try 41, and then eventually try 18. And if I look, command 18 is this: I want to read multiple blocks of data from the SD card. And then after that, I can just start reading through data, and eventually then I'll have to send it, let's see, it'd be a 12 that says I'm done. I'm done reading, stop transmitting, and that way I could send it some other commands and parameters. With this read block, for example, one of the parameters, which would be one of these sets of zeros here, is saying what address do I want to start at, and I'm just going to start at the beginning of the SD card for now. Later, I'll have to decide, do I want to mess around and I'm going to say bother with like FAT or FAT16 as a file system, or just use this more in a raw way. I'm leaning towards using it in a raw way. I might write a little utility that lets me nicely organize my stuff on there at specific addresses. It's pretty easy to use. I just want to know the address that something's at. And if I had 10 ROM images, I would probably just use a specific pattern that tells me where they're placed at. And maybe I'll even have a little index at the beginning of the SD card, like a really simplified FAT type of setup. Then here's an example of where I go in and I start reading, and I say read from the SD card, and I loop through. And what you're going to see here is that I'm just going to send it the first 1024 bytes of data. But that's what I'm going to read and send to my computer, I guess, in this case. So I kind of wanted to see, could I do what would a 1K chunk of data look like if I was going to pull it off the SD card in a raw format, and that's what I do here. And with that, let me go ahead and get over and show you some of that. So first of all, let me maybe turn on the system and just show you what it looks like. So I already have power applied to my power card. I'm going to flip on the rest of the system. And I heard it beep, and I'm not using this screen anymore. And instead, I'm going to be using this terminal screen. So I'm going to turn this off and flip over to this terminal screen. And I think I'll just go ahead and clear everything on it and kind of start fresh. And I'm going to even reset the Nano here. So if I just press the reset button on it. So the Nano is now sitting here waiting for me to send stuff to it. And I'm going to turn on the system, and I want to have port B grab data from the card, and then out of port A write it to the Nano, and the Nano then is sending it out USB and then USB serial so that I can see it here on the screen. And let me go ahead and fire that up. And so what you're seeing now is stuff that I've logged throughout the process. So as I'm processing that, I'm writing comments down on the screen. So here you can see I jotted down that I'm in the middle of the SPI and VIA initialization. And then I'm going to get into the SD card initialization, and I start it and I send it a command 0. And I didn't get the result I wanted. So I had to send it again. I sent it a second time and it was successful. Then I sent it a command 8 and I was successful on the first try, and a command 55 followed by a 41. I didn't get what I was looking for, so I had to do a 55-41 again. Then I did another 55-41 and then another 55-41, and then that worked fine. And right now, if I run this again, let me go ahead and do that. I want to hit reset. You might see a different pattern, and sometimes you'll see that you'll have fewer of these retries that you need to do. I would also say that if I swap in a different card, for example, you're not going to be able to see this very well, but if I grab this other card, this is a 32 gig card, and I think what's in there right now, let's see, is probably an 8 gig. So I've got an 8 gig card in there now. Here's a 32 gig card. If I put in the 32 gig, I see a different type of result. And for example, if I want to turn this off for a second, I'm going to go ahead and pop that card out, and I can pop this one in, and then I'll turn it on. And you'll see that when I went to read that card, it had to go through more of those sequences. And then, of course, the data is different. And there's also a different point at which it was ready to actually start sending me data. It took a bit longer for that card to be ready to basically stream data out to me. And I can see that card has a lot of zeros on it, and then some data. I don't know what that data on that card is right now. I think it has a couple of files on there maybe. I'm going to go ahead and flip back to that other card because that's the one I've been using kind of as my benchmark here. And I kind of know what to expect out of this one. Okay. But comparing those two, you can see different behaviors, and that seems pretty par for the course for SD cards. You kind of have to have some flexibility in your code to try things, and that's why you try it, check for the result, try it, check for a result. It depends on timing, it depends on a bunch of things, and that can make it frustrating when you're first trying to get this stuff running. But then I eventually get down here on this, and I send it a command 18, and then I just start reading bytes. And if I get an FE at the beginning, that tells me it's now ready to start giving me data. So the data actually starts right after that. And there I can see that that's my 1K of data that I pulled from the SD card and wrote out to this Nano. And then I get down and I say, okay, I'm done reading data. I finished command 18, and then all of my SD card routine is finished at that point. So that's the behavior I'm getting. Now keep in mind, I can still hit escape on my keyboard, and I test the math coprocessor, and I write out to this SPI device. So I can be doing all of this. I'm working with 3 SPI devices now. They're all working. They all seem pretty happy with the code that I've written. And if I quickly pull up that code, and just to show you some of that, this is going to get pretty long, so I'm not going to go through the code at all in detail. Maybe I'll just point out a few things. I did come in here and add some routines. So there is an SPI SD card initialization routine that I wrote. I have a routine to read data. I have a routine to send a command to the SD card. There's a slight variation of that where I tell it to keep the chip select low at the end of that command, which is not very common but is needed in some cases. I have a routine that says wait. So if I ask the card for something, I'm just going to sit and keep asking it until I get a response. So there's kind of a wait type loop. And then I have some routines to write out to SPI. And I separated them into one routine for port B and one for port A. I could probably consolidate these, but for now, I just copied them and modified the things inside of them that needed to be unique for port B versus port A. And then I have a command down here that lets me send to the Nano here, and basically I can give it a command number followed by a parameter or a value that goes, piece of data that goes with that command. Maybe let me just jump into, as an example, let's look at one of the routines that's a little bit longer, which is the initialization routine. So in this, here are the different values I'm using. I showed this in a print screen earlier. So for each of the commands, I'm just moving values into variables so that I can refer to that throughout the code. I could have done this, of course, in my ROM data, stored it there, but then I'd have to be switching my segment up to those constantly, and I didn't want to be doing all that switching all the time. So I just have some variables, CMD 0, 1, 8, 12, 18, 41, and 55, and then when I initialize the card, I just fill in manually the values there. There's got to be a better way to do it. I know if it's in my ROM space and I have something that constant, for example, that has this, then that adds a little hassle when I'm going into these routines. I did run into a little challenge there, though. Let me just show you, and anybody out there has suggestions on this. With that, I did also have to set aside some space so I wasn't stepping on my interrupt vector table. Without this code here, as I was filling in those other variables, I could tell it was stepping on where interrupts happen, where my interrupt vector table does something, so that it was jumping into my keyboard routine when it definitely shouldn't have been doing that. And so I put in this that just basically said, here's a K, 1K of space, which I think is the most I should need for the interrupt vector table. But just treat this as a bunch of zeros, and that way the other things that I have in here, if I understand how it works, and when I get into some of these other variables, they would be after that. Or if I talk about these here as I fill them in later, they're not going to step on that IVT. And I don't think I can use BSS because of where that places it. Maybe there's a better way to do all this. I did also try playing around with my registers here and having them start at a different address, but I wasn't having any luck there. But this ended up working well and has been solid. But if that's a tangent, but if you got any feedback on that, let me know. But anyways, I fill those in with all of the different commands and parameters for those commands. And then I get in here and I have to track all of these different chip selects. So right away I pull all my chip selects high, and I do that on port B, and I should probably do that on port A also. And actually it gets done in a different procedure. So let's see, I have a different procedure that would have been called previously SPI init. And in SPI init, let me just show you that real quickly. Here is SPI init. I do take all of these and pull them up. So all of my chip selects, I pull my clock signal high and the MOSI high, and I write that out both to port B's configuration and port A's configuration. So this is just which direction, my data direction type of register. And so I'm getting all that set up, and then I also set some initial values. So I say, what this is doing here is saying that if this is set, these are outputs. If they're not set, they're inputs. So you do not see SPI MISO, which means that's an input, and I'm configuring both of the ports that way. And then I set those initial values, and I pull all of these things high. So when I said I was pulling up high earlier here, this is actually setting the direction, and then down here when I write to the port, that's putting these values on that port. Then I get into this code, and the first thing you have to do with an SD card is you have to give it 80 clock cycles on the SPI clock. And so that's all this little loop is doing, is it's giving me 160 cycles, but each one of those is going up or down. So 160 up or downs put together is 80 full clock pulses for my SPI clock. And then I get in and I say, try this command 0. And so I log something out to my nano that just says I'm going to write a string that says I'm going to do something about starting, this first command of 00. And then I take that variable cmd 0 bytes, which has all of my command and parameter data, and I basically point to it with bx. And then I call this procedure send command. And what that send command is going to do, then it has to work through each of those pieces of data. And so I grabbed the first value, and because it was stored in a little endian, I grab bx plus 1 and I write that out to the port. And then I grab whatever's in bx and I write to the port. And then 3, 2, 5, 4. But that's going to take whatever I put in here and write out to SPI on Mosey. It's going to write out a 40, a 0, 0, 0, 0, 95. And that's the type of thing I have to go through. So then I have to send all of those out, and I do all that through the send command. At the end of it, I've got to pull my select line back up, whereas up here I pulled it down because I omitted it. So that's all the type of things you've got to do, is you've got to get your select line set correctly. You've got to figure out how you're going to write out, and you can again look at my code as far as what I have for writing out. Basically, it's just bit by bit writing these values out and toggling the clock, and then at the end setting my chip selects back to where they need to be. And then if I try all that and I get a return out of it that is a 1, and so that all works, then I'm saying, okay, that's great. I'm going to go ahead and continue on. If not, go back and try it again. And it's just going to sit here and loop until it gets a 1. And I suppose you could add some logic that after a certain number of times you just give up. But right now, this is just going to loop until it gets what it wants. Something else that I learned last time I was doing SPI stuff about a year ago, and I forgot, is that when I change my chip select from low to high or high to low, you're supposed to send a garbage byte before and after that change. So if I want to take my chip select high on one of my devices, I should send 8 bits of garbage, make the change, and send 8 more bits of garbage. It doesn't matter what they are, I just call it garbage, but you need to send some data. And I had forgotten about that. I was running into that with this here too. So that's what all that procedure does, is it's a routine that just sends out 8 Fs or 8 1s, FF if I remember right. It doesn't matter what you send though, you got to send something at the right time. So a lot of those are the details that I've been working through, and again, take a look at the code. It is far from perfect. There's a whole lot of just cleaning up I can do of the assembly itself. For what it's worth, I'll get it posted. And I think that's about it. Maybe I could go in here real quick to waveforms and just show you what this looks like. I'm going to go ahead and turn the system off. And maybe a couple things, and I haven't looked at this recently, so this might be a good test to see how good or bad things look. If I go to my protocol, I'm just going to clear that, and I'm going to tell it, start logging whatever you see. And what I'm looking for is to see if it screams at me about missing stuff. And amazingly, it does not. So that's great. That means it's not catching any major issues at the moment. So that's good. Let me go over to the logic here, and I'm going to go ahead and turn my system off again. And let me just set this at a frequency that would be okay. And I'm going to start scanning. And then I'm going to go ahead and turn my system on. I'm going to let it get sweep off and come back around. And I'll turn my system on, and just you can see what it logs here. Okay, so that was the entirety of getting the data filled in and brought out here. And if I want to look at this, I can see that, right away I've got, I can kind of look for the blips, right? So where's a blip? And there's a blip here, and that looks like it was just something probably during the power on. So I'm not going to worry about that one. I'm zooming back out. Then I got a blip right here. Let me zoom into that. That's probably going to be my 80 cycles of just initialization. And you've got to do that while probably Mosey is high and also all of your selects are high. So I don't have well, I say all of my selects, this specific chip here. But after I did my initial cycles here, then I'm going to go ahead and take a look, and here's my garbage byte that I send, and then I change my select line to low, a garbage byte, and then as I come to the right, I can see a 40, 0, 0, 0, 0, and then I think it's 95 over to the right. And if I go back to my code, that should match. If I go back up to those values, 40, 0, 0, 0, 0, 95. So that's what I sent it, and I can see that And this is probably hard to see on the recording, but this is just a lot of data to have on the screen. But then at the end of that, I get back a 1. So I send it some pulses and then get a response, which is a 1. And so, okay, I made it through that. And then I can now go to the right, and I can see I'm sending it 40,000,095, and that was the same one. So it must not have, I didn't get the result, or I didn't read the result fast enough that I was looking for. So we went through that and then got over, probably made it through that time, and now I'm sending a 48 down to AA87, and that would be this here that I'm sending, command 8. And at the end of that, I do have a 1 that I'm getting, and then I've got something happening on the clock line, and that's probably a different SPI device. This right here, I'm logging for specifically the SD card. And then I can see I'm sending it a 7700. Again, if I come back here and I look, where's my 7700? That's an app command, so a CMD55. And then this just continues through all of those ones I've sent. And then eventually this whole mess here is just all that data. So I would have sent it 52, and that 52 is I want to read multiple blocks. I send it the rest of my parameters down through E1, and then I just start saying feed me data, and I read a byte, read a byte, read a byte, and you'll see that this MISO is just constantly sending me back data. And the nice thing about this tool is it lets me see what I'm getting back for data. And so I can actually go through and read the values and see what am I getting, and does that match what I'm expecting to see. So there's that FE that I'm looking for to say, yep, you're actually getting data back from the card. And then I've got a 1D01003E. And I think if I go back over here, then that's this data right here. And if I go back to what was on the SD card, I don't have that handy right now, but back to that original screenshot I showed earlier, that should match what's on the actual SD card. And then somewhere at the end of all of this, then I should have had a call that kind of shuts things down. And there's my 4C whatever. And so I go back to my code, stop transmission 4C. And so that's where I'm sending that 4C sequence. So that's the type of stuff that I've got to do. And at the end of that, I stop selecting the chip. You can see along the way, there's times where I deselect that device. This whole sequence was all under 1. And then here you can see I'm turning on and turning off. And in between, I'm probably doing other things. For example, writing stuff to the Nano. That's happening. I'm just not connected to and logging that data at the moment. I would not be able to get SPI working without this type of a tool. It's just there's too many details, and coming in and looking at very specific timing of where these are coming out, rising or falling. And you really got to have things really in spec for this to work according to whatever device you're working with. And so that's what I've got there. I am curious why this all of a sudden has started coming on when I initialize, so I'm going to have to debug that later. I would not expect that, and I wasn't getting that before, so I don't know if I did something there. I just did a soft boot of it, so okay, it might have gotten confused somewhere with something, and which just tells me maybe somewhere in my SPI code there's something not quite perfect yet. So keyboard works, I'm looking at that. It's on the second line because somewhere in my previous code I told it to go to the second line. Escape still works, this comes up correctly. But see, now it came back with something there. So I'll have to debug that later and figure out what's going on the cold boot. It looks like if I just hit reset, the problem goes away. So there's some timing thing, and I'll have to figure out where that is at. Okay, that's probably plenty for this video, so hopefully that is interesting and helpful, and I'll get my blog post page updated with a link to the current code that I'm using. Again, this code is not great, but you should be able to kind of look through it and kind of see what I have and how I'm working through this. And for those of you that have done this and you have suggestions on better ways or major improvements in the code, let me know, or even minor things, let me know. I'll work on cleaning up this code as I move forward. So that's enough SPI for now. Maybe a future video I'll try to get the SPI to read an actual ROM image and get that ROM image put into RAM and shadow it. And I think maybe one of the next videos I have coming up too here is I should have this week the initial 286 PCB board that I had ordered. I think that's coming in this week. I've changed a lot in the design since that PCB, so this could get interesting, but I'm going to try to get it spun up and working anyways, and just to see if that PCB in general is looking okay, and then I'm probably going to order a revised version of that PCB pretty quickly. But that's it. So SPI done for the day. Thanks everybody for watching.